Hello and welcome to today's Titus Timeout podcast. I'm Jenny Civey and today's topic is on sound. We're just going to cover some basics of sound today. We'll cover sound data and applications in a later podcast. Let's start with the decibel. There's some very good detailed explanations of the decibel on the internet. For instance, Wikipedia defines the decibel as a logarithmic unit that indicates the ratio of a physical quantity, usually power or intensity, relative to a specified or implied reference level. For our purposes, you really don't need an in-depth understanding of the decibel itself, so let's simplify it just a little. Sound is a pressure wave. Sound intensity is measured in watts per meter squared. I'm not even going to write that down because you're not going to need it here in a minute. The intensity of a sound is different from the loudness of the sound as perceived by our ears. The perceived loudness of a sound is not proportional to the intensity of the sound. It's more like it's proportional to the log of the intensity. So that's where the decibel comes in. The decibel is a simple way to compare the loudness of two sounds. Technically, the decibel equals 10 log of the intensity divided by the reference intensity, where I.O., the reference intensity, is 10 to the negative 12 watts per meter square. Okay, so let's move this out of the way a little bit. You really only need to remember that it is a log function. The important thing to remember is that the decibel is measured against a frequency. The frequency of a sound wave is basically how many times it oscillates per second. Our ears perceive sound differently in different frequencies. Frequency is measured in hertz. There's an infinite number of frequencies. If you can imagine, there's 1 hertz, 2 hertz, 3 hertz, and on and on. So we group them into octave bands. For our industry, the octave bands are centered around increasingly wider frequency ranges, starting at 63 hertz and doubling from there. So octave band 1 is 63 hertz, octave band 2 is 125 hertz, octave band 3 is 250, 4 is 500, 5 is 1,000, 6 is 2,000, 7 is 4,000, and the 8th band is 8,000 hertz. Ran out of room here a little. There you go. Octave bands 4 through 6 are the speech interference bands, or also called the speech interference levels. This is because most human speech happens between 500 and 2,000 hertz. Having a sound too loud in these bands could make it hard for people to hear other people talk, hence the name speech interference. Different products generate their highest sound levels in different octave bands. Fan boxes, for instance, have their highest sound levels in the 2nd and 3rd band, while grills and diffusers create their highest sound level in the 4th, 5th, and 6th bands. You often see HVAC data shown in octave bands 2 through 7 only, because that's where the product's sound level peak. But in room design, high decibels in the 1st and 8th octave bands can also cause problems. Okay, so let's scoot this out of the way a little bit. As I mentioned earlier, we're more sensitive to certain frequencies. For instance, high frequencies, it's about 4th band and higher, the threshold for hearing is 20 dB or lower. At 4,000 hertz, we can actually detect sounds as low as 0 dB. But when it comes to the difference in sounds at high frequencies, we really can't perceive the difference less than 3 dB. We need about 5 dB to notice the difference between two sounds. 10 dB sounds twice as loud, and a 20 dB difference is 4 times as loud. So at 4,000 hertz, a 60 dB sound would be twice as loud as a 50 dB sound, and a 7 dB sound would be 4 times as loud. So now let's look at the low frequencies. In the low frequencies, that's 3rd band and below, the threshold of hearing is 25 dB or above. In the 1st band, the sound would need to be almost 50 dB before we could even hear it. In these frequencies, it takes about 3 dB to notice the difference in sound, two sounds. A 5 dB increase would be twice as loud, and 10 dB would be 4 times as loud. So going back to our 50 dB example, in the 2nd band, 55 dB would be twice as loud as the 50, and 60 would be 4 times as loud. So I want to touch on wavelength for a minute here. Let me redraw the octave bands and their frequencies. And then let's add a column for wavelength. The wavelength of a sound wave is its velocity divided by the frequency. The velocity of sound is 1126 feet per second. So if we look at the octave bands again, do the math, you come up with the wavelength of the first octave band is about 18 feet, the second octave band is about 9 feet, the third's about 4.5, the fourth is about 2 feet, the fifth is about 1 foot, the sixth is about 1/2 foot, the seventh's 1/4 foot, and the eighth is about 2 inches. Now if you visualize a sound wave, now that you know how long they are, you can quickly see how some sound waves, low frequency waves in particular, are too large to be absorbed by normal construction materials. For instance, the first band wave is 18 feet, that's larger than the average office. The second one is 9 feet, about the size of an office. The third band is 4.5 feet, that's larger than most ductwork. The fourth band is 2 feet, that's probably about the size of most ductwork. The fifth band is 1 foot, which is smaller than ductwork. The sixth band's about 1/2 foot, that's about the thickness of a wall. The seventh band's 1/4 foot, that's definitely less than the thickness of a wall. And the eighth band is about 2 inches, which is about the thickness of liner inside your ductwork. Now if you take a minute to listen to the sounds around you, this is why you can often hear the low frequency sounds of the air handler or fan boxes that are in the ceiling or even on the rooftop, but you typically can't hear the diffusers that are in the hall outside your office. So that covers the basics of sound. Thanks for taking a time out with us.